Yeah, ma'am. Yes.
Good morning, one and all virtually present here. On behalf of Electronics and Communication Engineering Department, we welcome you for the webinar on ASIC Design. I would request Nishmita to introduce our guest.
Hello, sir.
Yeah, tell me, ma'am.
Good morning, everyone. This is Bhishmita from ECE Department, third year. It is a glorious moment to extend my warm wishes on behalf of J.N.N Institute of Engineering. I would like to start by wishing you and your families my personal best for your health and safety in these difficult times. I am very glad to acknowledge our chief guest, Mr. Dr. Karthik Shekhar. I would also like to warmly welcome our Honorable Chairman Sir, beloved Vice Chairman Sir, respectful Principal Sir, our scrupulous HOD Joseph Sir, on behalf of Department of Electronics and Communication Engineering. I am very much pleased to extend my warm greetings on behalf of Department of ECE conducting a webinar on ASIC Design by a resource person, Dr. Karthik Sekhar. Now, I would like to speak few words about our chief guest, Mr. Dr. Karthik Shekhar. Dr. Karthik Shekhar has completed his PhD in the area of VLSI. His research area includes high performance computing, reconfigurable architecture, VLSI testing, DFT, low power VLSI techniques. He is well versed in HDLs like Verilog, VHDL, and also worked in many development boards like PI, PYCOM, ZDD, etc. He has published more than 20 international journals. He believes in lifelong learning. He was actively involved in projects such as low power pattern generation for BISI architecture, fault tolerant architectures, dynamic partial reconfiguration in FPGAs, and low power adders. To update his skill set, he has attended numerous training programs and workshops such as Cadence Training Program, workshop in FPGA-based system design using Altera EDA tools, and in advanced engineering optimization. And now, to take the session forward, I would like to call our presenter, Mr. Dr. Karthik Sekhar, to share his views, thoughts, and knowledge with us. Over to you, sir.
Thank you. Thank you, ma'am. First of all, I should thank Mayakannan sir for inviting me to this webinar. And also I thank the management of J.N.N Institute of Engineering uh, for conducting this webinar on ASIC design. So let me start. Hope the target audience are say the first years and to the final years of EC student. So if I'm right, then I'll be considering this set of participants while delivering my lecture, because it, of course, the presentation contains many technical terms and jargons. So I think we have even a first year student should able to understand what I'm trying to say. Fine. So let us go into the particular topic, ASIC design. Of course, you know, ASIC is application specific integrated circuit, right? So I'll be talking more on this particular the word ASIC while we go through this particular presentation. All right. To start with, can anybody like identify what the people are doing in this particular image? I know, of course, you are connected in YouTube platform, I know, but I'll just say the answer. Uh, these people are actually carrying a 5 MB megabyte hard drive, which was being shipped by the IBM during the year 1956, right? So this is a 5 MB hard drive, and now you know the size of the same capacity, right? Not even that MB. It's almost, even if you say the TB, the size of your say the hard disk or the hard disk with the capacity of terabyte, you know, it has come down to the size of a passport or like a small mobile phone, right? So that is the advancement with respect to the domain VLSI. And even I'll throw the some light on what is that VLSI is. And this is your first electronic computer. I think people can see it occupy the entire room. It was ENIAC during the 1946. And you know, the size of a computer or a laptop, you know, the size, how it has drastically come down, right? This is all because of the technology that we have brought in. And similarly, this is your Apple computer. And now you can see the size of your Apple computer, right? Right. Now let me just go through the timeline of electronic devices. Most of you know electronic devices are built from semiconductor materials. And why we go for semiconductor materials? You can actually control the conductivity in a semiconductor, right? You can switch on or off. In the sense, you can apply the voltage, say, while creating a channel for the flow of electrons, or you can switch off, or by removing the supply or turning it off, you can make the device to be in off state. So you can use semiconductor devices like an on-off switch. And of course, there are a lot of application with respect to semiconductor device, like you can use it for an amplifier, a regulator, and everything. So you might have studied basics of semiconductor devices, maybe in say in the 12th or 11th or 10th standard, even maybe 10th, 11th, and 12th standard. And even in your engineering first year or second year of engineering, you might have studied about the various devices, electronic devices like a PN junction diode, say the transistors, NPN transistor, PNP transistor, everything. So all this, of course, are made up of semiconductor materials. And N-type, P-type, you know, right? Majority holes and minority electrons in case of P-type, and majority electrons and minority holes in case of N-type. So with this, we started making so many devices, transistors, MOSFETs, and everything, right? And so in the year, of course, the 1940s, 50s, we started inventing transistors. And then people like Kilby, Jack Kilby, you might have studied about JK flip-flop. It's the person, Jack Kilby, who invented the first integrated circuits in the year 1950, right? Sorry, so when I talk about integrated circuit, please understand what I'm drawing. Integrated circuit is nothing but interconnection of all the transistors, resistors, capacitor in a single silicon wafer, right? So, right. So when I talk about integrated circuits, it's nothing but the integration of all resistors, capacitors in a common common silicon wafer. Then during 1960s, 70s, we started inventing processor. You know the processor, right? Processor, of course, as an arithmetic logical unit, you have a control unit, you have a memory, okay? Sometimes sitting inside the IC or sometimes sitting outside the IC, and you have a lot of peripherals being interfaced with the processor. And the processor, of course, is a general purpose one, right? You can build, write any application onto it, right? So processor as it is a pure hardware. Processor is as it is a pure hardware. One has to write a program or an application code into the memory, and the processor start reading it and executing it. So processor, of course, as I said, doesn't do anything as it only. It has to, like, you need to write a program, and the processor, like the instruction decoding unit starts fetching the instruction and start decoding, and the execution unit and starts executing. So you might have studied all this in, say, in the third year of your thing. So processor is, of course, a general purpose one, and we started inventing a processor which can handle floating point arithmetic operations, right? Suppose I need to multiply 2.5 into 4.5. So then I need a processor to handle this particular complex operations. So we started inventing DSP processors, mainly to handle floating point complex arithmetic operations. Then we started that is fabricating ICs for a particular specific application like ASIC. That's what I'm going to talk about. Okay, and also FPGA. So that I'll be talking later part of my slides. And then now we are in an era like we talk about what you call a system on chip. A system on chip is you think of all the say the microprocessor, FPGA, all the peripherals that is needed for the entire complete system on a single IC. So there is everything on the chip, system on chip. It's like a tiny computer. And of course, we have moved into the era of nanotechnology, where we started dealing with single electron transistors, and we have started replacing metal interconnects with carbon nanotubes, and that's it. And so this is like a timeline again showing with respect to the size of the transistor. So when I say size of the transistor, you think of, I think you might have studied MOSFETs, right? Metal oxide field effect transistor. And you might have studied about the channel length, right? Length between the source and the drain of the transistor. That's the channel length, yeah. Right? So that we call it as technology. That channel length is almost, say, for example, in the say in 2002, the length was 180 nanometer. The channel length was 180 nanometer. And say around 2008, it came down to 65 nanometer. And in 2015, it almost reached 60 nanometer. And if I ask this question now, what is the current technology? You can find, first of all, take your mobile phone, find out what kind of processor you're using in your mobile phone, and then find the specification of the processor. You just read out the specification, whether it can be a Qualcomm or Snapdragon, whatever. You just go through the specification of the processor, you can see the technology, the technology in which we are, it's almost 7 nanometer. That is 7 into 10 power minus 9 meter. Okay, you can't even imagine the size. You can't even see. Okay, it's very difficult to see the size, or even difficult to see the transistor. Imagine. So we are into that particular technology, 7 nanometer and below. And see the size of the chip. It's just a part of your thumb. Not just the image you can see, very small. Okay, very small. Right. So since I use the word VLSI, you should know what is VLSI. See, I talked about integrated circuit, right? Integrated circuit is bringing all the transistors, the physical components like resistor and capacitor being fabricated in, say, a common wafer, okay, common silicon wafer. So when I talk about VLSI, it's nothing but the level of integration. Level of integration is more than 10,000 transistors in an IC. So actually, we retain this word VLSI, even though we have actually reached the level of integration like billions of transistors. But since the word VLSI like being predominantly used, we are still using the word VLSI. Otherwise, you might have or we might have started using the word ultra square large scale integrated circuit. That's how the technology has grown up. So what actually this field or this particular domain actually does like you're going to design, of course, design as well as the manufacturing of integrated circuit. So whenever, of course, when I say design, there are various ways in which design, that's what you're going to talk about, what is ASIC and everything. The various way in which you're going to do the design. And of course, manufacturing is taken care by the fabrication industries. You know, the giant people are, say, the TSMC, Taiwan Semiconductor Manufacturing Company, and we have United Manufacturing Company, and of course we have companies, manufacturing companies in India, but not that particular full-fledged fabrication plant. I say, of course we have the manufacturing unit in India in all the research institutes, IITs, and of course in SCL, Chandigarh, everything. But that's not a full-fledged lab like what I say in Taiwan Semiconductor Manufacturing Company. Design, of course, we actually, India, of course, right, where lots of design engineers are available who work in the what you call as front-end design and back-end design. I'll tell you what's the difference. So of course, a lot of design engineers are in demand, especially digital and analog domain. A lot of design engineers are domain. So you can even think of this as an alternative of like your career thing. Maybe when you come to the say the third year or final year, you can even think of this particular field. Why can't I get into any VLSI industry like Intel, Cadence, Synopsys, Xilinx, Tata Elxsi, Honeywell. So they're all the pioneers in semiconductor industries, right? So please understand when I say talk about VLSI, it's nothing but design and manufacturing of integrated circuit. Quickly. So we are actually seeing so we started we had a transistor being invented in the late 40s and 50s. We started integrating, like we have our first ICs, and then we had a small ICs with say number of transistors 10. When we have say 10, then we would have seen this small scale integration. Hundreds we would have seen as a medium scale integration, and I told you like it's more than 1,000 and 10,000. We call it a very large scale integration, and even I told it has reached ultra square large scale integration, but still we are actually using the word VLSI even now. So what's the advantage when you want to integrate something? So when you integrate, of course, your design gets improved because of lower parasitics. Parasitics, of course, unwanted capacitor resistor formed. Maybe this word parasitic, when you start studying subject VLSI or ASIC in your elective, maybe in elective or a core paper, you might understand the word parasitic. Because now when we fabricate transistors, say using say diffusion layers of metal layers, unwanted parasitics will be formed, which actually lowers the speed of operation. So when we actually integrate this parasitics, right, like we'll be reducing the parasitics, and of course, say the speed. So of course, integration increases speed with lesser power dissipation, more density. There is more number of transistors, and you can have as I said, the technology when it gets improved, you can have a smaller IC. Okay. So again, this is some milestone by the IC industry. Maybe I'll just leave it for a few seconds, just to know the history. So Intel was founded in the year 1968 by the Murray and the Noyce, the friends who started Intel. And I want to talk about Murray in the next slide, who actually the person who actually predicted that the number of transistor gets doubled, okay, in the same square meter or square centimeter every 18 months. Yeah, he's a person who's a co-founder of Intel, Gordon Murray. Of course, he's the one actually predicted the you might have studied about Moore's law, right? So this is a Moore's law. Number of transistor per chip would go exponentially. It is true till now, because for example, say 18 months back, if you had say 1 billion transistor, now would have been almost say 2 billions of transistors. Right. So again, this is again like a timeline I want to show. Maybe concentrate with respect to the supply voltage and the technology node we are. So we have actually I told you this is up to 2014. We have the roadmap, but drastically it reduced the technology where I told you right in 7 nanometer. And even you see the supply voltage. Supply voltage, we are operating ICs below 0.5 volts. Okay, we are operating voltage. The operating voltage as the supply that you need to give to the IC is almost less than the 0.5 volts. Okay, now coming. Let us see. So when I say integrated circuit, so what is like when you see the classification, okay, you go to a market and say you buy a IC. See, all that ICs are actually nothing but standard IC. Okay, ICs which you go go to maybe you know all the famous Moore Market and everything, Ritchie Street. Yeah. So when you go to the Ritchie Street and buy an IC, see, that's all standard ICs. ICs which is already being manufactured and available in the market with a part number. For example, IC 7004 or IC 7400 or 7402. And we have flip-flop ICs, counters, shift registers, even all that are, we can group it as a standard IC. When we talk about ASIC, right, it's IC being manufactured mainly to target for a specific application. Got it? See, standard ICs, of course, you can use it to build any application, but I want a customized IC for my application. IC used only for that particular application. So microprocessor, something say IC, when I'm manufacturing a microprocessor IC, that's not for a specific application. Microprocessor is being built for a general purpose one. You can use it in your desktop or mobile or a laptop or whereas an ASIC is something want to start right from say the thing I need to design and manufacture. For example, IC used for a toy, IC used for a memory controller. Say maybe IC used as a maybe your IC being built for my embedded application like washing machine or TV. I don't want to go for a general purpose. I want a customized IC. Then I need to start building my own IC, right? Am I right? Then I need to build, because that's not, I don't want to take the ICs available in the market. When I start taking the ICs from available in the market and create a board, everything, that's going to be very, very big. I want an IC for my specific application. Then I have my my own design methodology, and I can have my own specification, and I can bring down the IC size to be smaller. Okay, right. So a standard IC, of course, I already told you, is the one that can be purchased by quoting a number in the market. So example, I told some keys, flip-flops, counters, process. Of course, a standard IC will be available in a data manual. Okay, you get a data manual with respect to the, like when you buy an IC. Okay, when you go for ASIC, it's mainly, I told you, it's mainly being built and being designed, manufactured to meet a specific application. It's not a standard IC. Please understand what I'm trying to say. Right. So I'll take you to the different ASICs available in the market: full custom, semi-custom, and programmable ASIC. But try to understand, or before going into that future slides, you please understand ICs that are built for custom purpose are typically classified as ASIC. Right. When you go for ASIC, when of course I don't have standard IC available for that particular. For example, I want to say an IC which is going to control the toy or whatever. For say, if I want to have an IC mainly for like when I want to build a robotic arm and everything, I need to build a customized controller IC. Then I have definitely it's not available in the market. Then I need to go start designing from from the beginning. So I go I go for ASIC when something's not available in the market, right? And there are a lot of choices when you go for ASIC. So what is the advantage when you go for ASIC? I told you, you can customize the IC. Since you're going to build for your own function, you can design, customize. You can miniaturize it or make it small, right? So that's the advantage of going for ASIC. And you can also, since you know for this particular specification you're going to build the IC, you can know how many transistors or how many, for what purpose you're going to target. So you can reduce the number of inventories and everything and build a customized small IC. Since I'm building my own IC, the space, even I can save a small space within that. And of course, Since I'm going to take extra care, of course, the power consumption, the performance wise, the IC will be better. Risk. See, the risk is, the problem is, suppose I want to build my own IC for the specific application. The only the risk I can say is time and the cost. Time, of course, when you start design, you need to say, for example, suppose you need to go for a standard cell design or for semi-custom. I'll be telling that about the semi-custom. So time taken to say from the design till the fabrication, the what you call as GDS file. The what you call as, we call that GDS file is the file that you need to give to the fabrication for fabricating the IC. So the entire flow, right, starting from the specification to design, simulation, synthesis, this is all the flow. Maybe I'll take maybe in the later part of the webinar, or I'll be requesting the management to give maybe another session, maybe in the next week, to teach you the ASIC design flow. I don't know whether I'll be able to finish the entire thing in an hour. So I may request the management to give another session where I can teach you the design flow, how I'll be designing my ASIC applications like the IC. So time. So it almost takes, say, 6 months to 1 year for my IC to be designed and manufactured. So I'm going to waste a year. That's one. Second, since I'm going to make only one IC, right, for that particular application, for example, a toy, cost is going to be more. Suppose I want to fabricate 1 lakh ICs. I'm saying about number of ICs. Then the cost per IC comes down. Cost per ICs comes down. But when I want to only produce only or manufacture only one IC, the cost will be more. So that is the problem or the disadvantage or the cons or pros and cons of the ASIC, right? So the time taken. Right. Now I'll teach you about the types of ASICs. Of course, they are classified depending upon the number of mask process. I'll just tell you, give a hint, what is the mask. See, mask, of course, you might have studied about the lithographic process. I write maybe, say, in your VLSI, when you study VLSI, or even the first year subject, when you start studying about, say, electronic devices or whatever, you might have heard about lithographic process. Lithographic process is creating an image on the substrate. So suppose I want to create an N-type layer and a P-type layer, the SiO2 layer and everything. So I'll need a mask. Mask is the place I exactly, say, for example, it's a glass, rectangular glass with specifically, like you have a space where you can pass the UV lights, right? So how will you create a mask? You need to draw layouts. I'll show you what the layout is. So from the layout, you'll be getting the mask information. So we are going to classify the IC with respect to number of mask, okay, or number of process actually needed during the fabrication. Full custom, semi-custom, programmable ASIC. To be in detail, so we have different types of ASIC: full custom ASIC, semi-custom ASIC, and programmable ASIC. Okay, and under semi-custom we have gate array and standard cell. I want to share a small analogy here so that you'll be understanding better, okay, what I'm trying to say. So, for example, a full custom ASIC. For example, suppose I want to eat chapati or roti. What I'll be doing? Better way. There are different n number of ways to actually eat chapati. N number of ways from making and finally like consuming it. Suppose I want to make chapati or roti, whatever. So I need to go take a vessel, take the flour, maida or whatever, take the flour, knead it, make a dough of the thing, roll it, heat the tawa, put it in the tawa and consume it. So the entire process, right from taking the flour to consuming it is the what you call as full custom approach. So what I did here, I made my own chapati or roti. I used my own ingredients, or like I selected the ingredients, right? I selected, for example, the different flour that's available in the market, whether it's Pillsbury or Naga or whatever. Okay, so many vendors are there. My own flour, salt also. The quantity of salt being added, everything is in my hand, and the way I prepare the dough, again it's my hand, soft or hard or whatever. So everything is in my hand. Am I right? Everything is in my hand till preheat, like heating and cooking it and putting it, and everything is in my. That's the full custom approach. Now, what is the advantage of full custom? Advantage of full custom is, I think, since you're watching, I don't know, maybe if it was a live interactive webinar, it will be very good. But anyway, so when you go talk about a full custom approach, the advantage of full custom approach, everything is in my hand. Performance wise, chapati, of course, I can make it tastier, different size, whatever size, right? That's it. So that's advantage performance wise. But the problem is time. Time taken, almost say I need to spend an hour or 2 hours or 3 hours to do the entire thing. Okay, now come about semi-custom. So in case of semi-custom approach or semi-custom, I can say this is an approach. Okay, approach for getting your IC being designed and manufactured. So in your semi-custom approach, I can think of, say you go to say Nilgiris or Reliance, where they actually already prepared rolled chapati dough, not the dough, the entire thing will be available in packet. So what do? You can buy it, straightly put it in the tawa, heat it, consume it. Hardly say maybe if the supermarket is available to you, or if you have purchased before, almost the time taken is going to be less than an hour, and even sometimes you get half baked chapati. Sometimes you get a bare thing being rolled and everything. You need to heat it both the sides, everything. Sometimes I get half-baked chapati. That's what I want to differentiate between standard cell and gate array. Gate array is half-baked. You're going to heat for a few more seconds to eat it. Standard cell, different sizes available, different shapes of the chapati or roti is available. Whatever size you want, take it, heat it, and consume it. Better way. So of course it's going to take 1 hour, semi-custom. Better way in the sense with respect to time parameter. Okay, time is programmable. Programmable is something I want to talk about. See, programmable is not thing. Straight to go to hotel, consume it. That's what I'm going to say. Programmable, of course, the word is different, but I want to classify it with respect to time. Programmable is go eat in a hotel, order for chapati, maximum 15 to 20 minutes. They will give you a plate of chapati, eat it. Now, so two things you need to understand when I want to classify ASIC. One, time taken. So full custom, with respect to roti or chapati, I told 3 days. Sorry, 3 hours. Semi-custom 1 hour. Programmable 15 minutes. So when I talk about integrated circuits, full custom takes 6 months to 1 year. Semi-custom takes 2 to 3 weeks, and programmable we can do it in 1 or 2 days. But performance, which is better, is full custom. Why? You are customizing each and everything. What kind of material I need to use? Not with the floor. Now I'm going to talk about the integrated circuit. What kind of material I want to use? Whether I want to go for silicon, I want to go for germanium, or I want to go for hybrid semiconductors, compound semiconductors. Then what methodology, the number of layers, the number of placement, orientation of transistors, everything is in my hand. Semi-custom, you take an help of from a tool. You're going to take help of tool and the available libraries. So you have a set of libraries where all the cells are being pre-characterized and pre-tested cells. So straight away you can use the cells to build the design. Whereas programmable, everything is tested, manufactured, everything in an IC form. Only thing is you're going to dump the design in the programmable IC. You're going to dump the design in the programmable ASIC. That's it. Okay. Let me now talk briefly. Okay. A full custom IC. Of course, I told you engineers will need to start right away from the scratch. From the scratch, they have to start design. They can't use which is the design or anything which is existing. Then that's not a full custom approach. Everything has to be done by the designer. Suppose they want to create a new, gates being used in the particular circuit, they have to do it. They can't use this existing libraries utilized in the circuit. Microprocessor is a good example. Why I'm saying microprocessor? Intel, Intel release microprocessor every maybe say 6 months to 1 year. They take a time gap of 1 year to release one processor because everything they customize and do it. So only the performance of the processor are good. Understood? The performance of the processor is good because they take much time, own proprietary tool, own logic cell which is being designed and manufactured. Everything. They don't even depend upon any vendor. They won't even use any pre-tested or pre-cells. They do everything right from the hand. Right. As I told, the full custom, you can have the orientation and placement, everything done by the designer. I just want to show you a glimpse. For example, I want to design this particular circuit. So this circuit will be drawn by the design engineer with everything characterized, draw the layout. This is not like a PCB layout. This is actually a layout drawn for the particular circuit using the layers. They use the tool, draw the N diffusion layer, P diffusion layer, wherever the transistor. I think layout of the drawing layout of gates and layout. You might be studying in the subject VLSI or maybe in the when you study ASIC, maybe as an elective in your third year or final year. So you have a better understanding of what is layout, because only after drawing the layout you will get the mask information which I was telling about during the lithographic process, right? You get the mask information from this layout. You have to, from this layout, you get the what you call as GDS file, what you call as Gerber file. Okay, this is called a Gerber design system file, which I need to give it to the fabrication people, which they will fabricate the transistor. You can't just give the circuit and ask them to fabricate. No, you need to give the specific file, which is called the GDS tape out. We call the tape out of the thing, entire design. As I said, when you go for full custom ASIC, suppose I want to go for tech, we have invented new technology. Okay, we have invented new, say, new transistors with lesser size, say below 5 nanometer. Then what happens? Existing ICs are outdated because they are with higher length and everything. So no other way. When there is something new, I need to adapt it, right? So I need to build ICs when the technology is new and there is no existing library available, or if the existing cell library is not fast, all the gates, say flip-flops, counters are available in the library. When I say library, don't think it's not something physical. Physical, of course, when I say physical, it's only after manufacturing. Cells are available in a, what you call as I'll show you what is a standard cell looks like. A standard cell looks like they know where the layer, p-type, layer, n-type, they will be characterized and tested, and the cells will, the information of the cells, technology information, and everything will be the timing, everything of the cell, particular information will be there in the library, like a software in the sense as a like a file, library file. Okay, you use the library file to use all the cells in that available, like your C functions, right? You might have about the functions available for C already, built-in functions. Similarly, we have built-in cells, so where you can drag and drop, or the tool automatically picks up the cells. No. Now, what I'm saying about full custom is, of all the cells are not faster, then no other way I need to go for full custom ASIC. So I'll go about semi-custom ASIC. A semi-custom ASIC, I told you there are two different semi-custom ASIC. One is called a gate array based semi-custom. One is called standard cell based semi-custom. So when you go for a semi-custom ASIC, is of course the designer will be using pre-characterized and sometimes pre-fabricated. When I go for gate array, it is pre-fabricated. When I go for standard cell based design, it's pre-characterized and pre-tested cells. So cells will be available in the library. So you start say writing you might have studied about hardware description language. That is a language being built to describe the hardware. You know, might have studied Verilog and VHDL. If not, definitely will be studying. So a language being designed or used or being built to design the digital on analog, even analog blocks. Okay, so you can write a Verilog or VHDL and you can feed in that particular code to the tool, and tool will pick up the cells necessary for that particular code what you have written, and you can arrange the cells. I'll show you in the next slides, and you can interconnect and get the mask information from that and give it to the fabrication people. So this takes maybe hardly 3-4 months when compared to full custom, maximum 1 or 2 months. So you go for semi-custom when I want my time short. Like for example, people like, you know what, the mobile like people like Xiaomi or any other Vivo, you know, they may go for this kind of approach because they want to release the mobile phones with different processor architecture, no, then and there, maybe every time. Then they may not use full custom, they even go for semi-custom based ASICs. So a standard cell approach is, I already told you, cells are available, standard cells. Why we call standard cell means height of the cell is common. Height of the cell, I'll show you. I'm having the diagram so that I can show you. Yeah. Can you look at the diagram? You can see no height of the cells, the green color, right? All are some logic cells. Either it can be gate, or either it can be a flip-flop, or it can be a counter or shift register, or even a small blocks like multiplexer, whatever. Height of the cell is standard, and width of the cell varies. Can you see the width of the cell getting varied everywhere? Width of the cell can vary. Height of the cell. That's why we call it as standard cells. And all the standard cells are being placed within VDD and VSS. Two blue lines, right? Everywhere you can see two blue lines. The cells are placed within the blue lines. And of course, the next step, of course, we're going to interconnect the cells. That one we'll see later. Okay. So a standard cell, they're going to use pre-designed and pre-characterized cells called standard cells. And example I told you, it can be a NAND cell, XOR, F, full adder, a comparator, even a small blocks, RAM block, or even a microprocessor. So they're all is there in the library. You need to use the tool, EDA tools. EDA means electronic design automation tools like Xilinx and Cadence. CAD like tools like CAD and Synopsys also. There are a lot of EDA companies where they give the tool for you to work on. So use the built-in library and then build the design, entire design, and manufacture and everything. So this is standard cells. You can see two metal VDD VSS, and of course you can see the N diffusion and P diffusion. Actually, this is a NAND gate being like layout of the NAND gate. So this information, everything will be there in the library. So you use standard-based design, as I told you. When you go for you want design to finish in within say 3 to 4 months, and you're going to get a help from EDA vendors and use the tool. This is like an example of a tool from the Cadence, where you do work with the placement of the cells, routing, and you do all kind of process the design flow. That's why I told I'll be taking a design flow. Maybe in the later part of the maybe next set of webinar session, I'll be taking the ASIC design flow. But I don't know, the time won't permit me to finish even the design flow. So advantage, only thing is when I want to go for standard style approach, I need to buy the cells. Buy from the library, right? Library in the sense there are companies which actually sells all this pre-characterized and tested cells. So one has to buy it and use it. Only thing is expense, of course, expense in buying the library. But once you buy, you can do a lot of designs, right? Now, I told you, right, half-baked. Half-baked roti or chapati, I told you, that is the gate array. Gate array is something not only pre-designed or pre-tested, they are pre-manufactured. Manufactured in the, the silicon wafer, but the packaging will not be done. Please understand, the packaging will not be done. They will be manufactured and left open. So one has to buy this, just give interconnection. Just give interconnection, give this, or you need to say where and all the interconnection will be coming. Of course, in again you start working with respect to tool. So fabrication people will do the interconnection, package it and give it. So a gate array is something like you have array of gates being built. That's called the base cell or the primitive cell. So we have channel-less structured gate array. There are different channeled gate arrays. We have a channel for routing. Okay, there will be a row. No, there will be a row of gate array, a channel, a space for channel. That is where the wires interconnection will flow. Next set of gate arrays, where again you can have the interconnection. A channel-less gate array, there is no channel. You need to do top of the routing. On the top of the cell, you will be routing the thing. So these are the different form of gate array based ASIC. The only difference is standard cell approach in gate array. Standard cell, they use only pre-tested and pre-characterized cells available in the library, whereas gate array is almost manufactured, fabricated, and left bare. They won't do packaging. You need to say what you need to what you like, where are the interconnection, and the fabrication people will fabricate the thing and give it to you. So this is, of course, I just want to show the picture. So small, they have zoomed this one base cell, and that will be replicated all over the entire array. So of course, they are not only pre-characterized tested, also they are prefabricated. So only customization, only what you do, interconnects. See, full custom, everything is customized. Semi-custom, partially customized. Gate array, only the interconnect are customized. Otherwise, everything is being done for you. So of course, I told you, right, gate arrays, you can have a fixed gate array, you can have a macro cell, which can be already fabricated, everything in a gate array based IC. So I'll be leaving the slides with you. You can follow. Anyway, next is your programmable ASIC. A programmable ASIC is something. Gate array, I told you, gate array is something you have where you need to do the packaging in the fabrication plant. Whereas FPGA is something IC is already available to you. But IC is like something like an IC with all the, say, necessary logic blocks and everything, but not programmed. You have to program that particular IC. You might have started hearing about the term, started hearing about the term FPGA, maybe like when you started studying VLSI, or maybe when you go through some article, you might have started studying about FPGA. See, FPGA, of course, we have nowadays SRAM based FPGA, memory cell. Now, why we use memory cell based FPGAs? Memory cell can be programmed that to a static RAM. You can write a 1 or you can write a 0. That means you can program the cell. See, you might have studied about before going through FPGAs, you should study what is the programmable logic devices, PAL, PLA. You might have studied that, right? What is PAL, PLA? They are all nothing but they are like AND plane and OR plane being manufactured and everything. Only thing is you need to blow the fuse, or you need to form the fuse between the two lines to realize your function. But they're all one-time programmable. Either you make it or break it, the function will be realized, but they're all one-time programmable. But whereas FPGA, you can reprogram it, reconfigure it as many times you want. So FPGAs are the most popular programmable logic devices. So when you see about a basic FPGA architecture, it consists of a lookup table and memory, SRM memory cells, where you can program the cells. And when you program the cells, that particular cell will act as whatever. For example, suppose the cell to be act as an AND gate, you can program it. If the cell wants to be acted like as an OR gate, you can program it. The same way, you can write Verilog and VHDL code or whatever programming language, and you can straightly dump the design into that particular FPGA. You can design or dump it into the particular FPGA, and you can start using it. Of course, FPGA will be used for two types. Prototyping. Prototyping is before suppose I want to test my design. Okay, I want to test my design. I can test it in an FPGA, whether it's working or not. Or sometimes even I can use FPGA in building my complete system. So FPGA is nothing but field programmable gate array. We already studied gate array. This is field programmable. Field programmable is not with respect to voltage. Field is the place where you work. Suppose I want to program the FPGA in my home. Of course, home is that particular field where I'm going to program it. So field programmers don't get confused. I'm not going to use any voltage or pass on the current or apply a electric field to program it. No. Field programmable means you can program it at your workplace. That is field programmable. Okay. So advantage of FPGA. Now I think I can hear what students can answering this particular question. FPGAs, of course, you can do it or dump the design, and you can have your own design being built into the ICs within a day. So time we have shortened down to 1 day. Disadvantage, see, FPGA size, everything is fixed. We can't reduce the size, right? So only thing is we need to give a trade-off to the size, but the time limit I can reduce. So even when you go Google FPGA versus ASIC, still there are a lot of debate going on FPGA versus ASIC. ASIC in the sense, of course, FPGA means programmable ASIC versus the full custom or semi-custom approach, what I'm talking. So when you say FPGA versus ASIC, they will say a lot of complex FPGAs have come, powerful FPGAs have come. You have all the memories, processor, everything is being just like a system on chip. Right? That's what I'm talking about, right? SoC. We have an SoC ICs where we have an FPGA. We can program it we have the processor. You have the processor being built, so you can have a complete system on a chip IC. But again, one thing I want to say: when you go for full custom approach, you have the time, and you can save time. You have a better performance when you start building your own full custom IC. But of course, I told time to manufacture, okay, or time to market, TTM, time to market. It's going to be around 8 weeks to more than that. Or if it's saying months, more than 2 to 3 months, or even more than that, because the time you take, design it, test it, manufacture it, everything is going to take time. Whereas when you go for FPGA, I can do it quickly. One thing is, once the design is ready, you can dump it and use it. But FPGA standard in with respect to size and everything, so that you should be taking care of. So that's the just want to talk about various the ASIC types, full custom, semi-custom. Okay, I just want to show how a structure of an FPGA looks. So you have a green color, right? So all the what you call as the logic blocks, or what you call as configurable logic block. That means you can configure it anytime. And you have a interconnection switch matrix, that is programmable interconnection matrix flowing in between. Okay, interconnects. So you can realize any function in an FPGA. But each FPGA has a limit with respect to size of how many logic blocks are available, how many IO pins are available. That you need to take into consideration while choosing an FPGA. While choosing an FPGA, there are a lot of parameters you should take into consideration. Okay, a lot of parameters you should take into consideration. So when you go for as a FPGA based or a programmable ASIC, fast to time to market, and proprietary design is something. See, when I say proprietary nature, if I program my logic into an FPGA and give that FPGA to someone, they can't find out what kind of design sitting in the FPGA. They can't copy it. Very difficult. They can't understand what is there, because see, I have dumped my design into an FPGA and give the FPGA to something. No one can understand what is there. And of course, nowadays the FPGA comes with lower power consumption and no re-engineering. Re-engineering means I don't want to re-engineering means maybe with respect to design, but not with respect to the entire process flow. No need placement or routing, nothing. No re-engineering when you talk about FPGA. And no ASIC risk in the sense, see, even a small bug in the manufacturing while fabricating my own IC will lead down to so much of loss. Okay. So for example, one single IC, suppose I need to manufacture it, cost say $10 million. All the $10 million will go if I found the bug later point of time. But whereas an FPGA, the only bug can be found in the design. So you can change it anytime. So no re-engineering, no risk involved when I go to FPGA. But only problem with respect to the FPGA, something is all the standard available. See, you're going to dump a smaller design into an FPGA, but the standard size of the FPGA is going to be bigger, and the design is going to sit in, say, some part of my FPGA. So other, it's going to be waste, no use. Whereas suppose I want to build the same IC for that same functionality, I can have it in a smaller manner or smaller fashion. So please understand, when I go for FPGA, when I go for ASIC, that is full custom or semi-custom ASIC. So this is the comparison of various types of thing, full custom, standard cell, gate array, and FPGA. So if time permits, I may take the flow. And what's the time? I think it's almost 12. I think we can close the session. But if the management permits me, I'll be taking the entire design flow. I just want to show the how the entire flow, ASIC design flow. For example, starting from right away, how to the manufacturer, starting from design till the manufacturing. I just want to show the flow. So this I'll be taking in the next session of my webinar. It's the management permits. Now the questions are open to you. Thank you. Sir? Sir, I've done with my webinar, sir. So you can ask me any question. I think the question should be available in the chat box. Or I'll just leave my email ID and mobile number to, I think it's going to be, sir, is there with your mic and sir. You can share, sir. You can share my email ID and mobile to the students, and I'll be helping them. Suppose if they want to do their project in VLSI or ASIC, or they want any kind of help with respect to say the subject or anything, I'll be there to help them. And even if they want to get into the core industries in VLSI industry, I'll just show them the way in which I need to. So thank you all. So it's
Thank
open.
you, sir.
Yeah.
Thank you, sir, for your valuable webinar. Now I would like to present vote of thanks. It's matter of pride for me that I got a chance to thank everyone present here. First of all, I should thank our honorable chairperson, vice chairperson, principal, and HOD sir for conducting this webinar to learn about ASIC design. Additionally, I should thank our presenter and today's guest, Dr. Karthik Shekhar, for sharing his knowledge and bursting our minds. And finally, I should thank everyone virtually present here for joining this webinar. Thank you, sir.
Thank you, ma. So can I leave?
Yeah, sir. Thank you, sir.